ਸਤਿ ਸ਼੍ਰੀ ਅਕਾਲ, ਗੁੱਡ ਮਾਰਨਿੰਗ, ਗੁੱਡ ਆਫਟਰਨੂਨ, ਜਿੱਥੇ ਯੋਗ ਰੀਡਿੰਗ ਐਕਸੈਪਟ ਕਰਿਓ। ਐਂਡ ਆਈ ਐਮ ਰੀਡਿੰਗ ਅ ਬੁੱਕ, page number 116, Gödel's type theorems from Turing's result. In my presentation of Gödel's theorem, I have omitted many details, and I have also left out what was historically perhaps the most important part of his argument, that referring to undecidability of the consistency of the axioms. My purpose here has not been to emphasize the axiom consistency probability problem, so important to Hilbert and his contemporaries, but to show that a specific Gödel's proposition, neither provable nor disprovable, using the axioms and rules of the formal system under consideration, is clearly seen using our insights into the meanings of the operations in question to be a true proposition. I have mentioned that Turing developed his own later argument establishing the unsolubility of the halting problem after studying the work of Gödel. The two arguments had a good deal in common, and indeed, key aspect of Gödel's result can be directly derived using Turing's procedure. Let us see how this works, and thereby obtain a somewhat different insight into what lies behind Gödel's theorem. An essential property of a formal mathematical system is that it should be a computable matter to decide whether or not a given string of symbols constitutes a proof within the system of a given mathematical assertion. The whole point of formalizing the notion of mathematical proof, after all, is that no further judgments have to be made about what is valid reasoning and what is not. It must be possible to check in a completely mechanical and previously determined way whether or not a putative proof is indeed a proof. That is, there must be an algorithm for checking proofs. On the other hand, we do not demand that it should necessarily be an algorithmic matter to find proofs of suggested mathematical statements. In fact, it turns out that there always is an algorithm for finding a proof within any formal system whenever some proof exists, for we must suppose that our system is formulated in terms of some symbolic language, this language being expressible in terms of some finite alphabet of symbols. As before, let us order our strings of symbols lexicographically, which we recall means alphabetically for each fixed length of string, taking all strings of length 1 to be ordered first, those of length 2 next, and then length 3, and so on. Thus, we have all the correctly constructed proofs numerically ordered according to this lexicographical scheme. Having our list of proofs, we also have a list of all the theorems of the formal system, for the theorems are precisely the propositions that appear as last lines of correctly constructed proofs. The listing is perfectly computable, for we can consider the lexicographical list of all strings of symbols of the system, whether or not they make sense as proofs, and then test the first thing with our proof testing algorithm to see if it is a proof and discard it if it is not. Then we test the second in the same way and discard if it is not a proof, and the third, and then the fourth, and by so on. By this means, if there is a proof, we shall eventually find it somewhere along the list. Thus, if Hilbert had been successful in finding his mathematical system, a system of axioms and rules of procedure strong enough to enable one to decide by formal proof the truth or falsity of any mathematical proposition correctly formulated within the system, then there would be a general algorithmic method of deciding the truth of any such proposition. Why is this? Because if by the procedure outlined above we eventually come across the proposition we are looking for as the final line in the proof, then we have proved this proposition. If instead we eventually come across the negation of our proposition as the final line, then we have disproved it. If Hilbert's scheme were complete, either one or the other of these eventualities would always occur, and if consistent, they would never both occur together. Thus, our mechanical procedure would always terminate at some stage, and we should have a universal algorithm for deciding the truth or otherwise of all propositions of the system. This would contradict Turing's result as presented in Chapter 2 that there is no general algorithm for deciding mathematical propositions. Consequently, we have in fact proved Gödel's theorem that no scheme of Hilbert's intended type can be complete in the sense that we have been discussing. In fact, Gödel's theorem is more specific than this, since the type of formal system that Gödel was concerned with was required to be adequate only for propositions of arithmetic, not for propositions of mathematics in general. Can we arrange that all the necessary operations of Turing machines can be carried out using just arithmetic? To put this another way, can all the computable functions of natural numbers, that is, recursive or algorithmic functions, the results of Turing machine action, be expressed in terms of ordinary arithmetic? In fact, it is almost true that we can, but not quite. We need an extra operation to be adjoined to the standard rules of arithmetic and logic. This operation simply selects the smallest natural number x such that k of x is true, where k is any given arithmetically calculable propositional function for which it is assumed that there is such a number, that is, some proposition of x, k of x is true. If there were no such number, then our operation would run on forever trying to locate the required non-existent x. In any case, the foregoing argument does establish on the basis of Turing's result that Hilbert's program of reducing whole branches of mathematics to calculations within some formal system is indeed untenable. As it stands, this procedure does not readily show that we have a Gödel's proposition like pk of k that is true but not provable within the system. However, if we recall the argument given in Chapter 2 on how to outdo an algorithm, we shall see that we can do something very similar. In that argument, we were able to show that given any algorithm for deciding whether a Turing machine action stops, we can produce a Turing machine action that we see does not stop. Yet the algorithm cannot. Recall that we insisted that the algorithm must correctly inform us when a Turing machine action will stop, though it can sometimes fail to tell us that the Turing machine action will not stop by running on forever itself. Thus, as with the situation with Gödel's theorem above, we have a proposition that we can see by the use of insight must actually be true. Non-stopping of the Turing machine action, but the given algorithmic action is not capable of telling us this. Recursively enumerable sets. There is a way of describing the basic ingredients of Turing's and Gödel's results in a graphic way. In terms of the language of set theory, this enables us to get away from arbitrary descriptions in terms of specific symbolisms or formal systems so that the essential issues are brought out. We shall consider only sets of natural numbers 0, 1, 2, 3, 4. So we shall be examining collections of these such as 4, 5, 8, 0, 57, 1, 0, 0, 0, 0, 3, 6, 0, 1, 2, 3, 4, 9, 9, 9, 9, 1, 2, 3, 4, 0, 2, 4, 6, 8, or even the entire set of natural numbers, that is 0, 1, 2, 3, 4, and or an empty set. We shall be concerned only with computability questions, namely which kinds of sets of natural numbers can be generated by algorithms and which cannot. In order to address such issues, we may, if we like, think of each single natural number n as denoting a specific string of symbols in a particular formal system. This would be the nth string of symbols, say Qn, according to some lexicographical ordering of the syntactically correct expressed propositions in the system. Then each natural number represents a proposition. The set of all propositions of the formal system would be represented the entire set n. And for an example, the theorems of the formal system would be thought of as constituting some smaller set of natural numbers, say the set P. However, the details of any particular numbering system for propositions is not important. All that we should need in order to set up correspondence between natural numbers and propositions would be known algorithm for obtaining each proposition Qn from its corresponding natural number n, and another known algorithm for obtaining n from Qn. Taking these two known algorithms as given, we are at liberty to identify the set of natural numbers n with the set of propositions of a specific formal system. Let us choose a formal system which is consistent and broad enough to include all actions of all Turing machines, and moreover sensible in the sense that its axioms and rules of procedure or things may be taken to be self-evidently true. Now, some of the propositions Q0, Q1, Q2, Q3 of the formal system will actually have proofs within the system. These provable propositions will have numbers which constitute some set in n. In fact, the set of P of theorems considered above. We have in fact already seen that there is an algorithm for generating one after the other all the propositions with proofs in some given formal system. Thus, we have an algorithm for generating the elements of P one after the other, perhaps with repetitions that makes no difference. A set such as P, which can be generated in this way by some algorithm, is called recursively enumerable. Note that the set of propositions which are disprovable within the system, that is, propositions whose negations are provable, is likewise recursively enumerable, for we can simply enumerate the provable propositions taking their negations as we go along. There are many other subsets of n which are recursively enumerable, and we need make no reference to our formal system in order to define them. Simple examples of recursively enumerable sets are the sets of even numbers 0, 2, 6, 4, 8, and a set of squares 0, 1, 4, 9, 16, and a set of primes 2, 3, 5, 7, 11. Clearly, we can generate each of these sets by means of an algorithm. In each of these three examples, it will also be the case that the complement of the set, that is the set of natural numbers note in the set, is recursively enumerable. The complementary sets in these three cases are respectively 1, 3, 5, 7, 9, and 0, 1, 4, 6, 8, 9, 10, 12. It would be simple matter to provide an algorithm for these complementary sets also. Indeed, we can algorithmically decide for any given natural number n whether or not it is an even number, or whether or not it is a square, or whether or not it is a prime. This provides us with an algorithm for generating both the set and the complementary set. Or we can run through the natural numbers in turn and decide, in each case, whether it belongs to the original set or to the complementary set. A set which has the property that both it and its complementary set are recursively enumerable is called a recursive set. Clearly, the complement of a recursive set is also a recursive set. Now, are there any sets which are recursively enumerable but not recursive? Let us pause for a moment to note what that would entail. Since the elements of such a set can be generated by an algorithm, we shall have a means of deciding for an element suspected of being in the set, and which, let us suppose for the moment, is actually in the set, that indeed if it is in the set, all we need to do is allow our algorithm to run over all the elements of the set until it eventually finds the particular element that we are examining. But suppose our suspected element is actually not in the set. In that case, our algorithm will do us no good at all, for it will just keep running forever, never coming to a decision. For that, we need an algorithm for generating the complementary set. If that finds our suspect, then we know for sure that the element is not in the set. With both algorithms, we should be in a good shape. We could simply alternate between the two algorithms and catch the suspect either way. That happy situation, however, is what happens with a recursive set. Here, our set is supposed to be merely recursively enumerable but not recursive. Our suggested algorithm for generating the complementary set does not exist. Thus, we are presented with the curious situations that we can algorithmically decide for an element in the set that it is actually in the set. But we cannot guarantee by means of any algorithm to decide this question for elements that happen not to be in the set. Does such a curious situation ever arise? Are there indeed any recursively enumerable sets that are not recursive? Well, what about the set P? Is that a recursive set? We know that it is recursively enumerable, so what we have to decide is whether the complementary set is also recursively enumerable. In fact, it is not. How can we tell that? Well, recall that the actions of Turing machines are supposed to be among the operations allowed within our formal system. We denote the nth Turing machine by T of n, then the statement Tn of n stops is a proposition. Let us write it S of n that we can express in our formal system for each number n. The proposition S of n will be true for some values of n or false for others. The set of all S of n as n runs through the natural numbers 0, 1, 2, 3 will be represented as some subsets S of natural numbers. Now recall Turing's fundamental result that there is no algorithm that asserts Tn of n does not stop in precisely these cases in which Tn in n in fact does not stop. This shows that the set of false S of n is not recursively enumerable. We observe that the part of S that lies in P consists precisely of those S of n which are true. Why is this? Certainly, if any particular S of n is provable, then it must be true because our formal system has been chosen to be sensible. So the part of S that lies in P must consist solely of true propositions S of n. Moreover, no true proposition S of n can lie outside of P, for it Tn of n stops. Then we can provide a proof within the system that it actually does so. Now, suppose that the complement of P were recursively enumerable, then we should have some algorithm for generating the elements of this complementary set. We can run this algorithm and note down every proposition SFN that we come across. These are all the false, so our procedure would actually give us a recursive enumeration of the set of false SFN. But we noted above that the false SFN are not recursively enumerable. This contradiction establishes that the complement of P cannot be recursively enumerated after all. So the set P is not recursive, which is what we have sought to establish. These properties actually demonstrate that our formal system cannot be complete. That is, there must be propositions which are neither provable nor disprovable within the system, for if there were no such undecidable propositions, the complement of the set P would have to be the set of disprovable propositions. But we have seen that the disprovable propositions constitute a recursively enumerable set, so this would make P recursive. However, P is not a recursive, a contradiction which establishes the required incompleteness. This is the main thrust of Gödel's theorem. Now, what about the subset T of n, which represent the true propositions of our formal system? Is T recursive? Is T recursively enumerable? Is the complement of T recursively enumerable? In fact, the answer to all these questions is no. One way of seeing is to note that the false propositions of the form Tn of n stops cannot be generated by an algorithm, as we have noted above. Therefore, the false propositions as a whole cannot be generated by an algorithm, since such algorithm would in particular enumerate all above false Tn of n stops propositions. Similarly, the set of all true propositions cannot be generated by an algorithm, since any such algorithm could be trivially modified to yield all the false propositions simply by making it take the negation of each proposition that it generates. Since the true propositions are thus not recursively enumerable and nor are the false ones, they constitute a vastly more complicated and profound array than do the propositions provable within the system. This again illustrates aspects of Gödel's theorem that the concept of mathematical truth is only partly accessible by the means of the formal argument. There are certain simple classes of true arithmetic propositions that do form recursively enumerable sets. However, for example, the true propositions of the form proposition of wxz f of f wxz is equal to 0, where f is some function constructed from the ordinary arithmetical operations of adding, subtracting, multiplying, and raising to a power, constitute a recursively enumerable set, as is not too hard to see. An instance of a proposition of this form, although we do not know if it is true, is the negation of Fermat's last theorem, for which we can take f naught to be given by. However, a set A turns out not to be recursive, in fact, which is not easy to see through, though it is a consequence of Gödel's actual original argument, thus which are not presented with any algorithmic means which could even in principle decide the truth or otherwise of Fermat's last theorem. And figure they have a picture. I have tried schematically to represent a recursive set as a region within a nice simple boundary, so that one can imagine it being a direct matter to tell whether or not some given point belongs to a set or not. Each point in the picture is to be thought of as a representing a natural number. The complementary set then also represented as a simple looking region. And figure 4.2, I have tried to represent a recursively enumerable but non-recursive set as a set with the complicated boundary, where the set on the one side of the boundary, the recursively enumerable side, is supposed to look simpler than that on the other. The figures are very schematic and are not intended to be in any sense geometrically accurate. In particular, there is no significance in fact that these features have been represented as though on flat two-dimensional plane. Okay, so they have pictures of schematic representation of recursively enumerable set, and they have another picture where highly schematic representation of various sets of propositions. The set P of propositions that are provable within the system is recursively enumerable but not the recursive. The set T of true propositions is not even recursively enumerable. Okay, so my next topic is the Mandelbrot set recursive, and I'm gonna continue reading it from there, page 124, in the next video.